All right, so let's talk about OllyDbg. You've already been using it somewhat. So OllyDbg is really old and out of date. It only does 32-bit code. The source code was purchased and rebranded as Immunity Debugger, which is very similar. But anyway, we're going to use Olly here for a while. You could just as well use Immunity or X32 debug or X64 debug. All of them have a very similar user interface because OllyDbg had the user interface that became popular. So you can load EXEs or DLLs directly into OllyDbg, or if the process is already running, you can attach to a running process. And then, so you just file open, launch your EXE, it will load the code and automatically stop before it runs any of it at win_main. Because you're putting in a debugger, presumably because you want to examine it, so it doesn't just run it, it will break at the entry point and let you see what's happening. Or you can attach to a running process, and when you do, it will stop that process with a breakpoint at some random place in its code. So it's a sloppier thing to do, but sometimes you want to do that. Very often, you analyze code, you wander off into some bad place where you don't know where you are, so reloading it with Control F2, or there's a menu item for it. I do this a lot. This reloads it and starts from zero again. When you fall off track and you're lost, just reload it. Control F2 will reload it. F2 will set a breakpoint. It's worth learning a few of these keystrokes to make it easier to navigate in OllyDbg. So the interface, here in this assembler, you'll see the assembly language instructions. And by the way, you have to be running on an Intel processor. If you are a Mac M1 user, you're not going to be able to use OllyDbg there. You'll have to get your hands on an Intel processor. You can use a Google Cloud machine, for example, or an Azure Cloud machine to get access to an Intel processor if you don't have Intel hardware. So over here you see the disassembled code. Over here are the registers, like EAX and EBX and the extended and ESP and EBP. Here's a place where you can just have a memory dump of any region that you find of interest. And here's the stack. The stack has return values to return from each routine to the calling routine, and it has other temporary parameters on the stack, local variables. So that's what the basic structure. Right, now you can, if you want to modify data, in the decompiler window, you can select a command, and when you press space, it will let you change this code. So that's something we're going to do in the demos pretty soon. You can right-click modify, you can right-click edit in the memory dump. All these panes you can edit. The only thing that is really rude is if you change things and you want to save a modified executable, the best thing is save it after every change. Because if you change something here, and you change something here, and you change something here, then you can right-click and there will be an option that says save all changes, and they're lying. What they mean is save all changes in this segment. Remember, there's a text segment and a code segment and a data segment. If you change things here, you're changing the text segment. If you change things here, you're probably changing the data segment. So if you change something here and change something there and save it, you're only going to get one of those changes. This drove me mad. It took me like years of struggling before I learned how to save modified files in OllyDbg. And the simplest procedure is just save it after every change. But technically, you could make multiple changes here and right-click in this window and save all changes, and they would all be saved. But if you're changing down here, you have to right-click in this window and save. It's a little bit rude that way. Like I say, it's a nice product, but every product has its gotchas. The memory map is extremely useful, and we've already been using it. We're going to keep using it quite a lot. This lets you see where things are loaded, and if things are not relocatable, then executables will always load here at 400,000. But normally, due to address space layout randomization, it relocates them to a random address. Notice that the first part is the PE header, which is always the first 1,000 in hex bytes, and then the text section is next where you have the executable code. And then you'll have R data and other things like relocation down here. And those are just laid out. They always start at even thousands, so the code on the disk is packed right together to make it small, but when you load it in memory, it takes each section and puts it separately in memory so it gets bigger. It leaves gaps between them to make them all start on even thousands. Rebasing is if you can't load code where it naturally wants to go, like every EXE wants to be at 400,000. Well, obviously, if you run one EXE and then you run another one, it can't load at 400,000 because that's in use. So it rebases. It moves it to another address. It then thinks it's at 400,000 as a virtual address, but it's really somewhere else. And if you support address space layout randomization, then every single time you launch it, it will randomly move you in memory to make it harder for an attacker to get in with a buffer overflow. Let me just check for comments, and there are none. All right. So DIL rebasing is another issue. DILs are very commonly relocated, and Windows DILs have different base addresses to avoid this. Relocating code technically makes it slower. It has to change things. Technically, it wastes a little time to relocate things, so Windows DILs assign a different base address to each DIL so they can more often just load at their preferred address. Although I imagine address-based layout randomization fouls that up. All right, so here's the absolute versus relative address. This code thinks it's at 400,000, so the executable code starts at 401,000. And as you can see, these are in the text section. And so if you have code like this, these instructions will work fine, but this instruction jumps to an absolute address, and therefore if you rebase this, putting in a different address, it's going to have to modify the bytes in this instruction. And that's the point. It's going to take more time to load, and that's why you have to have a relocation section which lists all the absolute addresses in the code and how to update them, which is what your loader has to do. So that's the point. DILs have a list of fix-up locations in the relocation section of the header. All right. And so here's a relocation section. You'll see here's a DIL, device metadata parsers, and if you open it in PEID, you can see the sections and see text, data, resource, and relocation. The relocation section is there to make it easier to move it around and run it at a different location. You can remove the relocation section if you want to. Several of our tools can do that. If you do that, it cannot be relocated. It would have to be at its base address. If that address is not available, it won't be able to run the program using that DIL. You'll get an error message. So be aware of that. Relocation technically wastes some time and is not preferred, but it is how things usually work. So here's DIL rebasing. DIL A and DIL B both want to be at this number, like whatever this is, 10,000, 1,000 or something. And so one of them gets that location, and DIL B has to move to another location. So this is going to have to use its relocation section and take more time to load, modifying all the code in that library to run at the other location. IDA-Pro does not run in code. IDA-Pro is a static analysis tool. It just looks at the code. Olly runs the code. You're looking at it in memory. IDA just looks at it. So IDA-Pro does not know about rebasing because it never really loads the code. It never worries about whether that memory is in use. So if you use both of these at the same time, you might get weird results. Like the addresses in IDA-Pro will be at 400,000, but the addresses in OllyDbg will be wildly different. So that's an issue to be aware of when analyzing code. You can view threads in Olly, and then you could, in principle, open them in CPU or kill them or something. I've never had to use this, but it is an option. Remember, modern code does not run with just one series of instructions. It has multiple threads that can move forward independently to avoid being slowed down by waiting for slow things like user input and network traffic. Each thread has its own stack in Windows. It can get pretty complicated, and you can see them in the memory map. All right, address-based randomization. In the last few years, people have begun to say that maybe it's not as big a security measure. It was great when Windows XP moved to Vista. They added ASLR, and it killed off a whole generation of buffer overflow exploits that had been deadly on Windows 2000 and Windows XP. But the attackers learned how to get around it with return-oriented code. So you use relative addresses to jump around. So people pointed out it's not that powerful a defense anymore, but it is built into every modern operating system. All right, so if you want to run code in Olly, you can use debug run from the menu, debug pause, breakpoint, or you can use hotkeys. F9 to run and keep running, F7 to execute one step, one instruction. Even if it's a call, it will make one step into the calling routine and stop there. Step over is very handy. It will make one step at the current level. If you're at a call, it will call and finish and return and stay at this level. This is very handy because if you do F7 a few times, you will almost always end up inside the Windows operating system. Every Windows function is really just calling the Windows operating system API calls to do everything. So if you F7 a few times, you're no longer in the code written by the developer, you're in the code written by Microsoft. And you very rarely want to look at the code written by Microsoft. Unless you are actually trying to find security flaws or bugs in Microsoft code, you probably don't want to look there. You want to look, for example, in the malware that's written by a malware author. So you probably want to use F8 to avoid descending into Microsoft library codes, which are not important. That's not part of the malware. That would just be for somebody who is looking for like a 0-day in Windows itself. All right. You can run, and you can click pause where it's where you want to be, but of course programs run fast, and it's unlikely that you'd be able to pause at the right time unless maybe you're playing a game and you can see something on the screen that tells you when you want to pause. Setting breakpoints is usually much better. Finding a location and putting breakpoints so you stop exactly where you want to be. You can run, and you can run to selection without bothering to set a breakpoint. You can just select an instruction and run to it, but this is breakpoints are more commonly used. That's all I've ever used. You can also execute until it's time to return. This is one way. If you do dig down into something like Windows API calls that you don't want to be in, this is one way to dig your way back up. When I have this problem, I just do debug restart and start from 0 again, but I'm only doing very simple jobs. If you're in a big complex job, you might want to recover without losing all your work that way. And you can also execute till user code. This is another good thing. This will get you out of the Windows API code and back to user code, so that's handy. So I said F7 is step into, F8 is step over, the next instruction at your current level. And this is risky. Something interesting might happen in there and you wouldn't know, and it might even get stuck down there and never return. And then it will never return after this, so you'll have to go back and try again. So let's try a Kahoot. AMD processors. Yes, AMD processors are fine. They're Intel compatible. OllyDbg 64-bit, no, don't use it. If you want to do 64-bit code, use x64 debug. Olly is not much use. Saw colorful balloons flying on my small screen. Well, I don't know about that. But anyway, all right. So let's see. I want to go here. It's a 9A, which is here. All right. All right. Boy, the heater's going hard today. Yeah, we have steam heat like from 1910, you know. Yep. Who was asking for feedback? I was? Oh, that's probably, yeah, that's overseen by one of my assistants. Good. Yeah, you don't like the banging. Yeah, well, believe me, it's better than last semester when there was no heat and it was just freezing in here. I had students showing up wearing wetsuits. Well, you would have liked it last semester then. Yeah. All right, yeah. All right, well, there we are. All right. Well, I prefer the heat. I was wearing like 3 pairs of pants and 4 shirts and a coat. But that's the thing about City College, the environment lacks luxury. You can't eat the price, though. That's the thing. I mean, you can pay $5,000 for a class, and then you get a much more luxurious environment. I've taught them, too. What's that? There are foreign students that pay full price, but you know, most people are getting in for free. All right. All right, so which objects are never rebased? Oh, okay, good. Yep, if you don't have the relocation section, then you can't rebase. All right, which key press will modify some assembly code? Spacebar. All right, what key press will step over? Very handy. F8, all right. All right, what key press will run until user code? All right. I can only do this one by elimination. I know what those are. It must be Alt F9. I've never used it. All right. Troglodyte will have to tell me who they are if they want their points. You know who that is, CF1212. That looks like that might be a real name, so those people, 2 or 3 of those will get their points anyway. All right, so let's go back to here. All right, so breakpoints. These are the types. I think we've talked about it before in general terms. F2 will add or remove a software breakpoint, which is typically that's all I've ever used. All the rest of these are for special purposes, and almost all the time a software breakpoint is good enough. So a software breakpoint will turn red, and what it means is OllyDbg has taken this, which is originally 52, and replaced it with a CC in memory. So when it hits that point, it will execute a breakpoint, but it has remembered in its Python code to put a 52 there if you run through there. So it modifies the image in memory and replaces it as you pass it. That's what software breakpoints do, and they're int3, as you can see down here. int3 is CC in hex. So software breakpoint is F2, that's the common one. You can have a conditional breakpoint, which will evaluate some kind of condition, like if the EAX is greater than 1,000, then break, otherwise don't, something like that. And you can have a hardware breakpoint, which does not modify the code. There's only 4 of them available, but they're in the hardware of the processor. This is the way you put in a breakpoint without modifying the code. And you can have memory breakpoints and memory breakpoints on access, which are implemented, again, by the Python code in the debugger. It really just makes a software breakpoint, but then when it gets there, it goes to Python and executes some commands to decide whether it really wants to stay broken, and automatically resumes execution if the condition is not true. So that's the game. And if you save OllyDbg, it'll save your breakpoints, which is a little disconcerting at first. When you open the same file again, it'll have the breakpoints. So that's a thing to be aware of. All right, so software breakpoints are extremely useful. For example, you've got this obfuscated code, looks like maybe it's base 64, but it might be something else. Then you call some decoder before it's used, so you can't find the strings with a static analysis tool like bintext, but you can find them by just putting a breakpoint after you call string decoder and then looking in RAM and it'll be there. So put a breakpoint at the end of the decoder routine, it'll therefore be on the stack, and that's really handy. You don't really have to figure out how they encoded and decoded it if you can just find the decoder algorithm. And that's why I'm often F8, F8, stepping through code, just looking at the stack, waiting for something interesting to show up. So conditional breakpoints will be here. In the book they talk about how poison ivy allocates memory, and you want to know when it allocates memory, a large amount of memory, because that would be when it's receiving shellcode from the command and control servers. So you want to break every time it allocates memory, but only if it's allocating like more than 1,000 bytes. And that you can do. On the virtual alloc function is the API call that allocates memory in Windows, and you can say break every time I call virtual alloc, but only if, here's the stack when it hits, showing the address, the size is here. This is only, I have 29 hex bytes. So that's a small request. So here I can just say, only the condition. If ESP plus 8, which gets you to that value, is greater than 100. So only break if you allocate a region with more than 100 bytes. That's the kind of thing you would do. So it sounds useful. In practice, I've never had to dig this deeply into things. And hardware breakpoints, like I say, are built in the processor. There's only 4 of them available, and they do not change the code at all. They're there for debugging. So that's an option. You'd use that if your malware watches for modifying the code. That's a way you can break code without changing it at all. All right, and memory breakpoints, Olly will do this. I think it's just a special case of conditional breakpoint. I think it does it with software. You can tell it will only break on access to memory or on read or on execute or other things. You can only set one memory breakpoint at a time. So I'm wrong about it. It implements memory breakpoints by changing the attributes of the memory blocks. I guess to create an exception when that happens, and that's kind of unreliable and has overhead, so that's another crazy thing I've never really used. You'd have to be in a pretty extreme situation to do that. But if you wanted to know when a DIL was used, you could go to the DIL's text section and set a memory breakpoint on access, and now it will break anytime it tries to execute the code in that DIL. So if you really want to know when it uses that library, that would be one way to see it. All right. Let's take a look at another Kahoot. There's a 9B, and apparently there's a 9C. I'll see if I can find that later. Black Hat, you pay like $3,000 for the class, and there's a table like this size for every 2 students, and like comfortable chairs and nice meals and everything, That's when your company's paying for it. Oh, it's nice. I can't afford to go except when they approve my classes. Then I go as a teacher. I'm not paying. But I did teach a couple workshops there, and it's nice. Including this class, I taught it there. All right, so what's the most common kind of breakpoint? Software execution breakpoint. The most common type, the only type I ever use. All right, which one is limited to only one? The memory breakpoint. You're only allowed to have one. All right, what key press sets a breakpoint? That's F2. All right. Which one has 4? library breakpoints. All right. So, all right. Let's use one twice. All right. I know who this is. Okay, so we can carry on here. All right, so loading DLLs. If you want to examine a library and you're not examining the exe that uses the library, you can load a library all by itself. What you do is you use loaddil.exe. And it'll break at the DIL main. Now, when you load a library, it runs the code in DIL main to prepare the library for use. And we're going to play with that in the demonstrations that are coming up. So it'll break there. You have to run DIL main if you want to use the DIL. And so I'm not going to bother demoing this live. It's not that exciting. But you can open a DIL directly, and it'll warn you. I can't execute it directly, so I'll use loaddil.exe, which is a Microsoft program for this purpose. And you say yes. And then if you try to call the DIL export, trying one of its exported functions, you can't because you have to run DIL main to prepare a DIL for use. So you have to reload it and then run once. And after you've run it, it's run DIL main. Now you can call DIL export, and you'll see a list of all the functions it exports. Here, this is a drop-down list that shows them all, and you can call any of the many functions, and there's typically hundreds of functions in a Microsoft DIL. It's crazy. So here's like the simplest one, network to host order. All this does is reverse the bytes in a 32-bit word. So this is an address in network order, 7F001. This is 127.001 in hex. It looks to me like it's missing a 0, actually. I think it should be 4 zeros there. No, well, yeah, it's missing 2 zeros. Anyway, you can reorder it with this function. And so, so this is the right one. I don't know, my image is wrong. 001, right, 4 bytes. This is in network order, so if you call this function and run it, the answer in EAX will show them reversed, 01007F. That's all this does, a very simple function, but one thing you have to do. So you could, in principle, call a function and give it arguments and see if that function works in Olly. I've never done this. It's something you would probably do, not so much for malware analysis, but actually for developing code, testing your code. But anyway, it's an option. All right, and there's also this tracing option, which is kind of nuts. You might, in Microsoft Word, when I first learned Microsoft Office, I was so happy with undo. You can do things, and you can undo like 10 times. It's magic. It's wonderful. I was so happy with that. That was so great. It was so powerful. You can undo everything, and you can put that in Olly. You can turn on tracing. You highlight an area and turn on tracing, and you can add undo. Now, it's very expensive, of course. There's a lot of memory and a lot of processing required for this, but you can do it. Now, there is something called a backtrace. You can use a minus sign to move back to the previous instruction, but all it does is show you which instruction it came from. It doesn't restore the registers or anything, or the stack. So it just shows you where it came from. The plus key would take you forward. You can do that just to see what instructions came before and after this one. But if you can do a call stack trace. If you view call stack, it will show you the call stack, and I'll demonstrate this when we get to the project. It shows you all the functions that were called to get here. So you started with Windows, then you called the main, then you called the print, then you called a library function. It'll show you the series of functions that you're currently in. You're in a function, you're in a subroutine, you're in a subroutine. That's what the call stack is. It's something you commonly see when programs crash. It prints out the call stack so you can see all the functions that are currently running and which line of code they were on, and you can hopefully figure out which line of code caused the problem. So, all right, and we'll demonstrate this a little later. Here's the entire main of this program. I'm going to demonstrate this one right after this. So here's a game that asks you for code and you don't know what it is. So we're going to hack the game. And this game is wonderful. The entire code is here. It's incredibly simple. And so we're going to be able to patch it. Anyway, if you step into here and view the call stack, here's an example of the call stack. So here you are at the module entry point. Then you're in, this is the local function, and now you're in put S. So you can see you're in this, and you're in when you return, you'll return first from this function and then to this function. So that's what the call stack is. It shows you all the return pointers to take you back out of where you are. All right. And so if you go in deeper, it gets higher. There's more steps to go back if you move forward. So that's the sort of thing. So here you'll see a series of functions there. And we'll play with this. All right. And by the way, here's a deeper one. I chose one of the lab functions, went deep. You can see, you're often very deep, many, many layers down. These are all the functions. So I was in ntdil, which is probably a library that lodged it, then this thing, then shell32, then this thing, then several things there. That's the thing. You're usually many, many, many layers deep in programs when you're running. And you can do a run trace, and this is what gives you the full Microsoft Word undo. You highlight code, do run trace, add selection, and now you can see all the instructions that were executed in the region you highlighted, and you can do plus and minus, and everything will update and follow it. So it can be done. All right. All right. You can trace into and trace over if you want to. All right. If you try to trace your entire program, that would take a long time and use a lot of memory. All right. And you can trace until a condition hits, just like you can have a conditional breakpoint. It has some of these fancy features for fancy debugging. But one thing, I've never used any of that fancy stuff, but what I have used, and we'll use quite a bit, is exception handling. Exceptions are when a bad thing happens, that the program cannot continue at normal execution. Like you divide by 0, you attempt to access an illegal region of memory, or something like that. It can't execute the instruction, so it raises an exception flag. And so the program will stop, and the exception will come to the debugger. Now, you can step into or step over the exception, or you can run it, because the first chance is just an exception happened and you return to the code written by the developer. The developer might be a good developer and include test conditions to handle exceptions. So Shift F9 will return that exception to the code, and maybe the code will handle it. If it breaks again, that means the developer did not include an exception handler for this exception, and the program is going to crash, and it's going to pop up a generic Windows exception. Yeah?
Is the structured exception handler in this at all? Or?
Yes, the structured exception handler is what was put in by the developer. So in Python, you do try and then except. Mm-hmm. And other languages have a similar structure. So if you consider it, then you handle certain exceptions, but there are unhandled exceptions. And so it goes to the exception handler, and the exception handler has a series of addresses which check if the exception is equal to this, then do that. If it's equal to this, then do that. If it gets to the end and it hasn't been handled, then it goes back and says, okay, this program is toast, and it pops up a box saying your program has crashed. And it offers to open the default Windows debugger, which is often WinDbg, if you have one at all. Yeah, very good. All right. And so then you can patch things, which we're going to do in the project. I'm going to do right after this. You can right-click code and assemble, or you can press the space bar. You can fill with zeros. You can fill with nops. You can copy and paste. But you can take code you don't like, and you can just change it to different code, of course, in the debugger. And you can save the modified exe if you want to. And this is how you do things like cheat at Windows games, and we're going to do that. All right, you can fill it with zeros. You can fill it with nops to skip instructions. And so, like I say, right-click, copy to executable, all modifications, save file. That's what you do to save it. Just do this after each change, or you will be miserable, like I used to be. Change 3 things, save it, and only some of the things get saved. Very disconcerting. All right, and there's a technique to analyze shellcode. Shellcode is code that gives you a remote control of the machine. So it's the egg, most malware. The goal is to put shellcode on the machine so you gain control of it. And so if you have hex shellcode, there are a lot of ways to analyze it. My favorite way to analyze it is just write a C program that runs the shellcode, and then use a C compiler to run it. That's the most common technique. But you can dump it directly into memory in OllyDbg and then run it directly in OllyDbg. I've never done it this way, but this is a way to analyze shellcode if you want to. All right. And there are some assistance features. There's a log. The log is quite helpful. The log shows you all the steps you used. It shows you how you got where you are. And we'll use it a couple times in the projects, mostly to show flags. You can also turn on something called watches that will watch an expression. I haven't used these in OllyDbg, but I've used them in WinDbg, where you can have a calculated expression that pops up. So you could watch for something. You could watch for file names in a call to create file, and then you'd see what files are being created by the program this way. All right, you can label things. If you're analyzing something big, you can add marks to it. You can label things and save the labeled things. So after you figure out this is the decoder, this is taking user input, this is the encryptor, that sort of thing, you can label them. And there are plugins to extend Olly. There's a bunch of them. The one we've used already is OllyDump that will dump a debug process, so it's useful for manual unpacking. There's one that attempts to hide OllyDbg from debugger detection. Some malware notices if it's running in a debugger and runs differently. You can control it from the command line. You can add bookmarks and so on. All right. And you can script it. Now, ImmunityDbg employs Python scripts. I guess Olly might not use Python. I'm not quite sure. I think it doesn't. That's right. Olly, I don't know what Olly uses. It's not Python. Immunity uses Python. And then you have scripts and PyCommands. So we'll be using Immunity later in this class and using some of those scripts. The main one we're going to use is Mona. Mona is extremely useful to perform return-oriented programming. And I guess we might not use it in this class, but we use it in the exploit development class. Anyway, let me see if I can find the last cahoots. They are not in order, which is one of the limitations of the Kahoot system. However, if you sort them into folders, then it's not too hard to find them. Computers and phones, they pop up some noise as if I'm supposed to know something. Anyway. Cars, too. They turn on mysterious lights as if I'm supposed to know what that means. Hopefully, with AI, our devices will start talking to us and saying things we can understand instead of just popping up like a yellow exclamation point. And I'm supposed to know what that means. All right, so if you press the minus sign, what's going to happen? That's a backtrace. It will move to the previous instruction so you can see where you came from. All right. If you want to step back and see the register values from the past, what you do? That's a run trace. All right. Gives you the undo. All right, what feature shows all the functions that are waiting for execution to resume? That's a call stack. That's what that is. Call, 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 call. All the things that have been called that have not yet returned. All right. What feature shows you all the modules that were loaded before the current one? log will show you that, all the libraries and modules that were used. So,